electric field is a vector quantity, and this is related to negative gradient of the voltage. This is a potential difference. Now, what if I want to define voltage? Everyone says, well, hey, what's voltage? Well, here's voltage. Voltage is actually what we define as the integral. So say that you have a certain charge in your pocket and you march from infinity to a certain reference point. So here's infinity, here's a reference point. I call sigma, here's sigma right there. This is the integral from infinity to sigma of E dot do. So it's just the amount of work that you kind of have to do. The units of voltage right here are actually joules per coulomb. So it's the amount of energy you do per charge in your pocket. Remember, by the work energy theorem, if you do energy, you do work. Okay, so what you do is you're very sneaky, you put a little charge in your pocket, you go from infinity, you go to a certain reference point, and then this is what we call voltage. Now, what it's in the wall right here, 120 volts, that's not this voltage, that's a change of voltage. So this is going to demonstrate that. This right here is actually, do you all know what that is? It's a gradient operator. Oh, look, we actually messed up. That's actually a vector quantity. And so what does this actually mean? Well, in one dimension, you can have this, right? If you have any curve, doesn't matter what it is. If you want to know the slope of this curve, what do? Well, you kind of just take the regular slope, right? So you take y2, y1, x2, x1, right? So then you define the slope as the change in y over the change in x, right? But what we want to do is we want to define the slope of an instantaneous point. We call this the slope of the tangent line. Right now, if I just look at these 2 points, that's actually the slope of the secant line. It goes between 2 points. So you take the limit as delta x approaches 0. And this gives us something that we call the derivative, dy by dx. Okay, now this right here.
Practicing their doctor.
Yeah, I know, right?
I know, totally, exactly. And I'm wondering if you should drink any more coffee.
I know, but this guy right here, this is a 3-dimensional derivative. So actually what this is d, and it's a partial. D by dx plus d by dy.
Doctors now are working by the hours.
Oh, well, this actually, this actually it actually looks like this. It's actually a little comic because it's almost like you take like an inner product, or who's in charge of what's the other name for an inner product? Dot product, right? Okay, so what we can do is we can actually split this up into 3 different components and call it the gradient. So instead, well, what if I don't have a line? What if I have a curve? What if I have like a hill? What do? Well, you take the gradient, and that tells you the steepness of the hill. Okay, so here we go. Electric field voltage. Next board. Here we go. If we go into 1 dimension, let's just say, for our sake, 1 dimension, we're going to say that this is the displacement vector. So I'm just going to change this right here. I'm going to say that the electric field that and look, I'm not even going to look at the vector. Who cares? I'm looking at the magnitude. The electric field equals the change in voltage over the displacement right here, delta x. This is the displacement right there. Now that's a neon sign transformer, so the voltage is approximately 15,000 volts, joule per coulomb. This is going to be meters. One of the units
I love
for
that you trust that.
no, I know. I was like, ooh, right now. Electric field actually has 2 units. It's newton per coulomb, but this is the same thing as a volt per meter. Same thing. In normal atmospheric conditions, if we can reach an electric field of approximately 3 times 10 to the 6 volts per meter, you reach electric breakdown, which is just when lightning occurs. So we're actually going to see that. So 15,000 volts. Now we might have to kind of play with this Jacob's ladder to see if it will actually work and why. If this guy's too big, you don't get electric breakdown. You don't get any lightning. So let's go ahead and
now do we get to see the pretty light?
Yeah, but you have to see the math before. But nobody cares about the math.
We do. But
I care about the math. Nobody else does.
I was too busy sitting next to the cute girl.
Yeah. You're like, oh, okay. Okay,
I
let's
was
see.
completely.
So did you say 15,000
Oh,
volts?
yes.
Yeah. 15,000. Okay, so it stopped. It just means that the displacement's a little bit too big. So let's try it again. There it is. All right.
Who's going to do the best
So what do you get?
young drinker?
And so what you're actually seeing right there is ionized nitrogen. I'm not sure if you guys know what this type of curve is. Well, you can have this type of curve where I call this the energy and this is the displacement or delta x. For hydrogen, it looks like this. And we say that this energy is 13.6, negative 13.6 electron volts. What does that mean? To ionize hydrogen, you have to shoot 13.6 electron volts of energy added. For this nitrogen is about 15, so it's a little bit more energy, but that's okay. It just depends how you play with the electrodes. Sometimes it works better, other times it doesn't. And then sometimes they get tissues, put them at the top, and then do you see the different color right there? That's ionized sodium. Now be careful. If you touch this one, what will happen is that your muscles will contract and you can't let go as it electrocutes you to death.
I nearly touched them.
Yeah. This is the only dangerous thing that, and this is actually my personal one that I built.
I'm watching.
Are these just copper too? Copper wire?
Yeah, just got them at Lowe's. This Pantograph does